Hi, welcome to es301 Engineering Analysis. This is chapter 5 and the topic is bracketing methods. So here are the learning goals. At the end of this video, you will know what is the root or the roots of an equation. You'll understand the difference between open and bracketed methods for finding roots. You'll be able to implement the bisection method for estimating the root of an equation. You'll be able to implement the false position method for estimating the root of an equation. And you'll be able to calculate the approximate error at each step of that method. So first I want to go ahead and just talk about what is the root of an equation. And the root of an equation, the definition I come up with, it's the value of the independent variable such that the function value will be 0. So sometimes roots are also called the zeros of an equation. Okay, so for example, let's say I have this equation here where I have f that's a function of x. And I've got this polynomial here. Now there's particular values of x that if I was to put that in here, this function right over here would evaluate to 0. Now that's not always the case. You could have a function that never evaluates to 0. So it's sort of a caveat, but often you do. And so what I would like to do is to go ahead and find out what are those values of x. All right, well, here's a graph of what this particular function looks like. And so if you look at my axes here, which are both crossing at 0, 0, you can quickly find out where the function is equal to 0. Clearly it's right there, it's also there, and it's also there. In fact, it turns out there are 3 roots to this equation. Now one of the things you can tell is if you've got a polynomial equation like this is, where you've got x to a bunch of powers, 3 is the highest power. That tells me I'm going to have 3 roots of this equation, or 3 zeros. Now they're not always different in this equation, they are all different. Sometimes they may be repeated roots. But here I want to go ahead and find out what those values are. Graphically it's pretty simple. I can look here, if I plot the function, just put it into Excel for example, I see it occurs there at 4, it occurs there at 2, and it occurs there at -2. So those are my 3 roots. If I was to put 4 in here, and for all 3 of those values of x, this function would be equal to 0. So it would kind of be the graphical method. Let me also mention you can almost always rearrange an equation so that it's a function equal to 0. So say that this right over here originally was this function was equal to 36.98, and you wanted to find out the value of x such that the function equal to 36.98. Well, all you would do is just move this over here, subtract 36.98, and then make that equal to 0. So you can clearly always make a function equal to 0 and then go ahead and find the roots or zeros of that equation. Well, we're going to look at 2 different numerical techniques. So these are not graphical techniques. Numerical techniques go ahead and find the roots of an equation. In this video, we're going to be discussing bracketed methods. In the next one, we'll talk about open methods. But first, I want to kind of explain what's the difference between a bracketed and an open method and when you can use one or the other. So for example here, this was the plot that I had before, and we had our 3 roots. And so if for some reason I knew that, for example, the root was going to occur in this region here, I could go ahead and bracket it and know that it's going to occur somewhere in that region. Okay. Sometimes you'll know that, sometimes you don't. And one of the things is that actually often plots look more like this. This would be more like a function that you might have in engineering, where you've actually got what would be called a monotonic function, meaning that there's only one root, and it's always increasing in one direction and decreasing the other. And this is a pretty common situation that you have. So you only have one root in here. Now, if you wanted to find it, a lot of times you'll actually know what the limits are. You can easily say, oh, I know it occurs somewhere between here and here. And I can put limits on that, and then I can implement what's called a bracketing technique. And bracketing techniques are very stable, meaning you'll always go ahead and find the solution as long as the 0 occurs somewhere in between that. Let me go through a couple examples of why you might actually know what the limits are. So here's a problem that arises in thermodynamics where what we're looking for would be called the adiabatic flame temperature. So this is an engine cylinder, and so right after this spark plug fires and the fuel in here burns, this material in here will be at a very high temperature. And so this is a problem where when you implement this, you'll often be trying to find out what is that temperature. And you do it with an energy balance that you can set equal to 0. And you try to find the temperature, but it turns out to be this kind of complicated polynomial function. But you can bracket what the temperature is. I mean, clearly you know at the lower level, it can't be any colder than, say, for example, 0 Kelvin. Nothing can be colder than that. And then if you wanted to know what the upper range could be, well, clearly if this is occurring in some sort of steel engine, you know it's got to be less than the melting point of steel. Okay, now that might seem like a really big range, but that's actually pretty small in terms of it. And so now you're actually able to bracket what those temperature is. So you can use a bracketing method that, as I mentioned, is very stable. Let's look at a couple other examples. Maybe this is from environmental engineering where you've got some dissolved ions in a river, and you've got a problem where you're trying to find out what is the concentration of that. And this is, again, another instance where, well, I know the lower limit is 0. It can't be negative. You can't have a negative dissolved ion concentration. And where else could it go? Well, it could go up to the saturation, and clearly dissolved ions can't be at a higher concentration than the saturation concentration. So once again, I'm able to bracket this and know what the range is. Let's just discuss one other quick example which we looked at before. And here would be, this was our skydiver, and we were trying to find out what the terminal velocity is. Well, again, you could probably imagine what would be the limits on here. Well, his velocity can't be any less than 0. He can't be going up. So clearly, his terminal velocity's got to be something greater than 0. And where would it go up to? Oh, I don't know. Maybe the speed of sound. He's probably not falling any faster than the speed of sound. And so again, you're able to bracket. So this would be a point where you could use a bracketing method. Now the opening methods that we're going to look at the next ones are when you can't put bounds on that. You actually do not know. You really have zero idea where that occurs, and so you've got to kind of find your 0, and you have no idea where it's going to occur. And we'll look at that in the next video. But here we're going to look at bracketing techniques, and we're going to look at 2 different techniques for doing that. So first what I'm going to do is I'm going to discuss the bisection method. And so the way the bisection method works, and so here I've got my independent variable, it's called x, and I've got my bounds, I know what it is, it's going to occur between, the notation we'll use is xl for x lower and x upper. It occurs somewhere between those bounds. And so what I do now is I go ahead and take that function, some function of x, evaluate it at x upper, and so maybe it's this point here, so I'll call that f of x upper, and then I'm going to evaluate it over and figure out what it is. And so at the lower limit, maybe that's right there is what f of x lower is. This is a positive value on the right, -1 right over there. And so now I'm trying to guess where the function crosses this 0 axis. And so what I could do is, well, first I'm going to do is I'm just going to go ahead and guess that it occurs maybe somewhere in the middle. I'm going to call that x sub r. I'm kind of sticking with the notation of the textbook. And then I'm going to evaluate the function there as well. So that might be, what is f of x r? So now I've got these 3 points. Remember, I don't know what my function looks like, so I can't find out where exactly it crosses. But looking at those 3 points, you clearly recognize it has to occur over here in the left-hand side. And the reason that you know that is because f of x lower times f of xr is less than 0. I've got a positive number times a negative number. So what I do is I can just set up kind of an if-else statement. If this is true, what I'm going to do is I'm just going to move my upper point over to xr. I'm going to change xr to x upper. Otherwise, I would move xl over there. And now I'm just going to do it again. So now I've got my new x upper. I'm just going to look for something in the middle, call that xr, and then I'm going to continue to evaluate that, and again determine which place it happens. Maybe here is f of my new xr, so again I'm going to move x upper over, and I will keep doing that. Now at some point I need to stop, and you might say, well, when are you going to stop? Well, if you could actually get what f of xr exactly equal to 0, you would find it. Now one of the caveats is with digital computers, you're probably never going to get equal to 0.00000 to an infinite number of precision, and so you can just get really close. So what you want to do is you want to get an approximate error. We don't know what the true value is, but we can get an approximate error. And so what we'll do is we'll just use 2 guesses of xr. So I'll use xr previously. So this point right over here, like the first guess, maybe we would move that to x previous. And then I'm going to take a difference between my new xr value, and then go ahead and normalize it by xr just to give it to me in a percent. So what I'm looking at is the difference between 2 guesses normalized by the absolute value. So maybe go ahead and express that in terms of percent. And as those get really, really close, I'm not modifying my value very much. And now I could say I'm going to have a stopping condition. of which when EA, or epsilon A, is less than epsilon S, I will go ahead and stop. So that would be a determination of when I want to go ahead and stop. This is a point where you never know the true error. I mean, if you could go ahead and knew what the exact value was, you wouldn't bother with the numerical technique. Now, one of the things about bisection is that it's easy to implement. We just kind of saw there's just you're just evaluating that function at several points, but it can be a little bit slow. And let me just kind of show graphically how that could be. Imagine that this was my function, f of x upper, and maybe I went ahead and evaluated f of x lower, and it was just some number that was barely below 0. Right? So again, I can still bracket it, but what would happen is I would first guess here. That would be step 1, step 2, step 3, step 4, and what you realize is it actually takes a long time. When I shouldn't have ever guessed that it was at this point, clearly it's going to be somewhere down there. And so I probably would want to go ahead and make my second guess, or even my first guess, somewhere closer down toward x lower because it's fairly close to 0. So that's what we're going to discuss next, which is a different technique, which is called the false position method. Right. So here's where the false position method works. And so, so again, I'm going to use the example that maybe this is x, f of x upper is over there, and this point over here is f of x lower. And if you evaluated those two functions, you would guess that, well, it's probably somewhat closer to the left than the right. And so I'm going to go ahead and guess a value of xr in the middle. And the way that I'm going to do that is I'll just assume the simplest thing, which is my function might be linear. And what I'm going to do is, if you look, I've got essentially two similar triangles here. And I'm going to go ahead and I want to find out what this value is, which is my value of xr. I'm going to use the law of similar triangles, right? Essentially, the rise over the run is the rise over the run there. So what that would be saying is that f of x lower over xr minus x lower, so the rise over the run, is going to be equal to, and it's going to be this function up here, f of x upper over x sub upper minus x sub r. Right? And so that's going to go ahead and tell me now I've got this function, it's of xr, and I'm going to go ahead and rearrange that equation to find out what xr is. The book gives you this equation. I'll just go ahead and write it here. If you were to go ahead and rearrange it, it's what you've got here now is your ratio between x lower and x upper, and then this bit over here is f of xl minus f of x upper. Anyway, that equation is in your book, but this is just solving this equation right over here for xr. There's my new value of xr that I would guess, and so at each step you'll actually converge on your answer fairly quickly. A little faster than the bisection method, particularly when it's skewed like this. And last thing, approximate error, you're going to go ahead and evaluate the same way you did before, which is just the difference between your two guesses normalized by your current guess. So you don't really have an error estimate when your very first guess because you really don't know how close you are. So there's no value for the approximate error at step 1, so you'll always have to implement this 2 times. All right, so let's just go ahead and go through an example. And first, let me just kind of give an engineering type example problem that you might run into. And so this is from the world of thermodynamics, and maybe the thing we're trying to determine is what's the temperature at which the value of entropy is equal to this particular value. Okay, so if you're not familiar with what entropy is, it's a measure of disorder, and it's used in thermodynamics, particularly when analyzing mechanical devices like this turbine that I'm showing here, because it turns out that if I have a very efficient turbine, the entropy is constant as I move through, and so if I knew the entropy going in, I knew it was 24.59, that would be the same value over here, and maybe I'm trying to find out what the temperature is at the outlet. So what I know is this value of entropy. And one of the things about entropy is you can get these correlations as a function of temperature, and I show an example one up here, and they're fairly complicated, they're very nonlinear. And again, what I'm trying to find is the value of t where I know the value of s. It's 24.59. But I don't know what t is. It's just kind of this guessing game. And so this is a perfect example of when you want to go ahead and use one of these bracketed techniques. And again, I can bracket here because I know the temperature is probably, well, it can't be any less than 0 Kelvin. And if I'm running a steam turbine here, I know it's going to have to, this is a steel turbine, it's got to be less than, the melting point of steel. And so now I'm able to bracket it fairly quickly. Okay, so if I want to go ahead and implement this, let's go ahead and use the bisection technique to do this. And I'm going to go ahead and implement this in MATLAB. And so here I've got my MATLAB code. And what I'm going to do is just kind of point out some of the important parts of this code. I can go ahead and post this online if you'd like to see it. So the top here, what I have is I've just went ahead and defined some values. Here's the entropy value I'm trying to find. And then I've got my bounds. I'm saying x lower is something between 1 and 20,000. And the reason I used 1 instead of 0 was because I have a log term in this equation. You can't take the log of 0. But 1 Kelvin is pretty darn close to 0. And again, I know that this has got to be greater than 1 Kelvin. And then I'm going to go ahead and I don't know my initial value of XR. I'm just going to initialize it to not a number. And you'll kind of see why. This is sort of just an implementation in terms of MATLAB. And then I'm going to go ahead and have my error, and I'm going to assume that my error starts off at 1. All right, so now what I've got next is this big while loop where I'm going to continue to implement the bisection method until my error is less than some stopping condition. I'm calling my stopping condition 1e to the minus 2, or 0.01. Okay. So the first thing I'm going to do is I'm going to set my previous guess of XR to the current value of XR, and then I'm going to go ahead and find my new value of XR, which is the intermediate between X upper and X lower. And now I've got just a little bit, this right over here is just a little bit of error checking. What I want to do is I want to find out what the error is, but you don't know at the very first step. So that's why I originally defined XR equal to not a number, which then gets put into XR previous, just so I don't evaluate the error when I don't know what it is. I don't have two values. So that's just kind of again, a little numeric issue. My next 3 lines right down here is what I'm doing is I'm evaluating my function at the lower point, the upper point, and the middle point. And I'm using this entropy function. What that entropy function is the one on the upper right. And I'll go ahead and show you the MATLAB code that for a second. But I put that in a separate function just to kind of clean this up. And then that's evaluating to a value of entropy. I want to go ahead and find the 0 of the function. So this is where, again, I'm moving it to the other side. I'm subtracting out that value of entropy value. So I have to evaluate that 3 times. And then what I'm going to do this next display, I'm just going to go ahead and just print to the screen so I can see how my technique is working. You can go ahead and see how those values change. So I'm implementing my values of X and what the error is. Again, here's a little bit of error checking. I want to make sure that when the user started this, that he didn't specify an upper and lower, where the 0 didn't occur in between it. So I just do a little check that X upper and lower is got to be less than 0 if I take the product of those. That's just a little bit of error checking, so go ahead and tell the user that they didn't give me good bounds. And then the last thing I do, this is where I move my new value of XR. So I either move X upper or move X lower, depending on which side of it occurs between 0, and then I'm done. And so I just go ahead and keep looping through. Here's that function entropy. This would be in a separate file. It's a fairly simple function. All I've done is just implement that equation right in there. It returns the value of S. So it just kind of cleans up the whole thing, and so I could go ahead and use any type of function I wanted in there. All right. If I was to go ahead and run this, so I called my script bisection method, and I go ahead and run it in MATLAB. Here I've got my plots, and just to remind you, the left hand over there was X lower, the upper one is X upper, the third one is what XR is, and then the third one is my fourth column is the error. And so what you see is initially I'm moving the upper point down, and then at some points the left one starts moving up. My error takes a while to decrease until it starts getting close, and then finally here's my step right here where the error is finally getting down to 0.01, and so I can go ahead and stop. So I would implement this one more time if I wanted my stopping error to actually be less than the approximate error. I'm sorry, the approximate error less than the stopping error, which I defined at 0.01. Okay. So just going to review what we talked about in this video. We went ahead and just defined what a root is, and the root of an equation is when the functions are equal to 0. We saw that bracketed techniques can be used when you know the upper and lower bounds, which is pretty common in engineering. We often can give ourselves some sort of bounds. The bisection method, we saw it's easy to implement, but it can be slow to converge. And so there's the false position method. It's a little bit faster, slightly more complicated formulation of that. So, all right, well, that's it for this video.